Next up we have Andrew Rawson, who's a senior consultant at Marico. Andrew's going to talk to us about the probabilities of vessel impacts with infrastructure.
Thank you. Just to give a quick overview of what I want to talk about, I'm going to do a very, very quick introduction, but most of it's going to be spent looking at a variety of different ways to consider the probabilities and the likelihoods of effectively vessels having accidents. So I'll give a quick overview about risk and probability. I'll then talk about the role of navigation risk assessment in design to try and reduce that probability, to design out risk. But as I say, the bulk of it will be dealt on statistical and analytical methods, really quantitative ways of looking at risk. So, don't need to explain this. Very simple equation, think about risk. Very focused on likelihood today. But many vessels have accidents. We just heard that the MAIB very busy investigating lots and lots of incidents that happen around the UK. Collisions, contacts, groundings, many other types of incidents that take place. But clearly these incidents have negative consequences. If you're a developer wanting to put in a new development, for example a new pier or a wind farm, whilst your development may pose a risk to other vessels pose a risk to your development. So it's a two-way process that you want to mitigate out risk. If you build this designing out process in the early phases, so you can design out that risk, it can save substantial amounts of cost. One of the things about the marine environment is it's very complex. You have lots of different actors all interacting with one another, all have different agendas, and you have a very complex environment with lots of environmental conditions which can increase that complexity ever further. So it's challenging even in the base case to understand what's going on. We're starting to predict what would happen if a new development was put in place. We're starting to change that environment. The complexity increases significantly further. So navigation risk assessment really is a way, particularly associated with the navigation of vessels and the ways that that can go wrong. So this is the IMO's formal safety assessment approach. So it's a structured, systematic type way of thinking about navigation risk. So you start by identifying what can go wrong, what are the hazards. Then you go through your process of risk assessment, looking at trying to identify the likelihood and consequences of that hazard. Whether it's safe or not, you'll start to want to think about risk control options, so ways of reducing that risk to acceptable levels. And deciding which risk controls to take further requires some cost benefits, understanding costs and the benefits associated with that. And all of that feeds into recommendations you make to decision makers. So whether it's the developer or the regulator. So many different things pose hazards. There's a few popping up here. So we've got wind farms, bridges, oil and gas installations, lots of types of things that need to be considered. So the maritime industry is quite an old industry, and a lot of attention is placed on the expertise and the knowledge of the people involved. So the master's experience and the harbour authorities' knowledge of their waters. So a lot of risk assessments are done based on expert judgment, and that has a place. There's significant value that can be obtained from that type of approach. But quite often data isn't really the driving factor, it's more a supporting factor. So it's looking at incident data that's been collected and what does that inform us about. But what I'm really going to start to talk about is maritime risk analysis. So the use of analytical quantitative methods of trying to put numbers to things beyond just judgment. So I think that there's kind of an escalating scale of different ways of doing it. So the first one's very much a statistical approach, and that's looking at incident data primarily. What does the incident data tell you? The next one is a further static approach, so it's looking at the geometry of traffic. It's looking at where the traffic lanes are and where they are in relation to a development. What is the distribution? Thirdly, we're starting to move into much more complex dynamic modelling type approaches where you're trying to replicate the marine environment through some sort of simulation. And fourthly is full bridge type simulation. So you're moving from a system-wide perspective more to a vessel-based perspective. What does the passage plan of the vessel tell you? So I'll start off with some statistical analysis. So incident data. So we can use incident data. If everything was perfect, we could look, well, what is the chance of an accident happening? We look over the last 10 years of data, how often has it happened? Therefore, that gives us some sort of knowledge of the probability of an event happening. And there's lots of different ways we can gather data, MIB reports, statistical studies that have been done industry-wide, academic research, or a port zone database. But there are quite a lot of limitations with this. I won't go through them all, but quite often you find that the past isn't a very good guide for what's going to happen in the future. Circumstances change. And particularly if you're going to put a new development in place, that completely changes the environment. So your historical data isn't quite as relevant as it could be. And then you can use all sorts of different things to try and get over this. Example here is the Heinrich pyramid. So trying to work out what the probability of a very rare event, such as a major capsize and huge loss of life, which is very rare in the industry, from more minor industries, more bumps and scrapes. But as you can see, you can build it up from near-miss data, but near-miss data is generally quite underreported. So you run into problems just using data alone. Now, to the risk of this being very Thames-centric, just a bit of analysis of the historical incidents on the Thames. So this is much of central London. As you can see there, this is sort of the area we're looking at. And this is some work we've been doing previously for some navigation risk assessments on the river. And it's combining historical incident data from the PLA's database with also vessel traffic data. So what we're trying to look at here is what is the rate? So how likely is an incident given sort of a unit measurement, what per movement? So if we just took it from a very simple level, where are all the contacts? This is vessels hitting infrastructure or bridges or piers, for example. So where are they actually occurring per year? Well, you can quite clearly see that there's quite a clump of them between Lambeth Reach and Upper Pool. And this is the central London area, so we're talking from, say, Westminster to Tower Bridge or so. So there's lots and lots of incidents going on there. But is that the riskiest place? So if we start to look at where is the vessel traffic? So here are two different measures of vessel activity. So at the top we've got kind of a measure of exposure. So how long do vessels spend in each of these sections of the river? And below it we've got the number of transits through each of these sections. So they show kind of similar patterns. There are some examples of where it's different, for example, Lower Pool, but part of that's explained by some of these areas are larger than others, some of them vessels are travelling faster, so they spend less time in them, and there are various reasons. But generally we can start to see that actually the central section is one of the busiest. So should we expect that there are the most number of incidents there? So if we just divide one by the other, very simply, where are the most number of incidents per unit of transit, per hour or per transit? We start to see that one thing clearly leaps out at us. Barnelm's Reach seems to be the riskiest, but that kind of throws up the limitations of your data. So a lot of this vessel traffic data that I've done to support this is based on the AIS system, which is a transponder-based system required on commercial and passenger vessels. So once we start getting to these upper reaches, there are less of them, given the amount of recreational craft. So rowers and dinghies don't carry that sort of equipment. So you're starting to skew your assessment. So if we just say this is an anomaly given the types of vessels there, we just look at the rest of them, you can start to see a much more varied picture than, remember at the beginning it was 90% of them or so were occurring in Lambeth Reach, King's Reach, Upper Pool. We can start to see a very different pattern emerging. And there are lots of different reasons for this. So this sort of rate is quite often referred to as a causation probability. So what is the chance that an incident's going to happen per unit? So some sort of unit measure of vessel activity. And this is quite important when we start thinking about more complex risk models, because a causation probability is generally built into it in one form or another. And we'll return to this in a minute. So just looking at some other probabilities. So I have here from another study. So these are the probabilities of a vessel contacting with a bridge that it's passing through based on 21 different studies. So these reflect different bridges, different configurations of channel. You can start to see there's a huge variance between these different studies. And as I say, there's lots of possible reasons for that. Clearly, the probability of a vessel hitting, I don't know, Tower Bridge is going to be very different from hitting the Golden Gate Bridge in San Francisco. So there is a lot of variance that local conditions need to be able to be picked up on. And that's kind of a warning on causation probabilities, that you quite often see studies that use very generic probabilities. And I picked up two here, which I see again and again, that have been based in Dover Straits, the Japanese Straits, from 30, 40 years ago. And what is their relevance to today's environment? So that's based on data. I'll just move quickly on, but there are many other ways of looking at causation probabilities through the use of whether it's Bayesian networks, more probabilistic analysis, fault trees. So what are the interconnecting events that can result in an incident? So that's looking at a statistical approach. So now I'd like to move on to what I call a geometric approach. And this is where we start building in what is the geography of traffic, what is the geometry of traffic lanes. So I have an example here which is probably quite typical of what people are doing, where if you imagine a vessel traffic lane, a route, from that lane you've got a distribution of traffic. So you've got lots of vessels in the lane and a lower probability that the vessel is going to be much further out of that lane. So if you've got an obstruction within that lane, or you're going to place an obstruction in that lane, there is a proportion of vessel traffic that are now in the path of that vessel. So a very simple geometric model would be that the risk is equal to the number of vessels going down that lane, what proportion of those vessels are now at risk, and what is the probability that a vessel that is at risk doesn't get out of the way. So they don't see it, or they have a mechanical failure, for example, that prevents them from avoiding that obstacle. This is quite a simple geometric approach. One example of where it's been used, I don't know if anyone knows about the IALA IRAP tool. There's many other different approaches. We use it, many other companies use it. It's a nice simple way of approaching risk. It's quite static, which we'll come on to in a minute. So I really wanted to show one of actually infrastructure, but various commercial sensitivities sort of prevented that. So I've recycled one from a presentation I did earlier in the year. And this was looking at the probability of a vessel hitting a reef off New Zealand. So some of you may remember the MV Rena in 2011, about 18 knots inbound on the port of Taronga, went straight into the Astrolabe Reef and eventually disintegrated over time. So what we were interested in was, could you build a geometric model which showed the before and after change in risk as a result of that incident? So these are the traffic distributions of vessels passing the reef. You can clearly see that before the incident happened, lots of vessels were, the dominant sort of flow of traffic into the port of Taronga was sort of about a mile to the north of that reef as they came in. Afterwards, it clearly changed as vessels were a lot more wary of that reef and they started to spend a lot of time further to north, and also various risk controls were put in place to prevent such an accident occurring again. So you've got two very different traffic distributions. So can we look at what the change in risk has been? How effective have those risk controls been preventing a future accident? Well, if we run it beforehand, so we've got the geometric probability of a vessel at risk, got some likelihood rates based on previous incidents. We get a return rate of about once every 5 years, so quite a rare event. As soon as the incident happened, you get a massive change in the probability of a reoccurrence. So we get about a 4-fold change in risk. And this stayed quite constant for a few years, until 2016, when it actually got even less. Now, we weren't able to know exactly why, but possibly the introduction of virtual navigation around New Zealand's coast. So that's it. We're starting to put numbers to this potential risk of a reoccurrence that previously hadn't been done before. So that's geometric, so that's very static. So thirdly, I'd like to talk about modelling. So much more complex, much more dynamic. So as I said earlier, maritime domain is a very complex one. So if you want to represent risk in this domain, there is some argument that you want more complex models to be put in place. So what we're trying to develop here is a way of thinking about how are the different actors interacting with themselves almost in fast time and with their environment. So I'll just flash that up just for the interest of time. But there are advantages and disadvantages to doing this approach. Clearly, once you increase complexity, it becomes much more difficult, much more time consuming to do. So there is an element of proportionality in terms of the complexity of the question you're trying to answer. But just as one particular example, so this is our temperature traffic model we've worked with the PLA for, really looking at trying to understand risk in central London. So I'll just flash this up. It's going to work. Yes. Okay. So this is just a 2-hour period, looking at the interaction between different vessels. So where are vessels coming close to one another? And this really picks up the themes that we've heard about trying to use near-miss data and incident data. If you've got very little incident data, you want to try and look at these near-miss occurrences which aren't being reported, and starting to look at the interactions between vessels, trying to grade the severity of vessels coming close to one another, you can start to make inference that you didn't have beforehand. So this particular type of approach is called domain analysis. There's many other ways of doing modelling. So this starts to answer questions on risk. So where are vessels coming close together at speed? And you can also answer other questions. So questions on capacity. If you look in certain sections of the river, you can see it's quite quiet, and then a couple of minutes later it's very busy. So that really emphasises that it's a very dynamic problem you're trying to solve. So whereas the previous approaches, such as incident data and geometric approaches, are very static, this one's more dynamic. It may well be more representative of what's actually going on. Yeah, so you can start highlighting where vessels are coming close to one another, where they're coming close to particular types of infrastructure at speed. So finally, I want to take a very different tack almost. So these have been, what I've presented previously, have been very system-wide approaches. So looking at the whole study area and trying to infer risk from that. This one's much more focused on the individual vessel through full bridge simulation. So what we're starting to answer here is the feasibility of a particular passage with, for example, changed conditions. So one particular example might be if you want to test whether which bridge span option is the safest for a particular type of vessel passing up your river, then running full bridge simulation is a way of engaging with masters and pilots to understand, well, what are the pinch points here? How close are they getting? How comfortable are they feeling? And you can start to test that under a range of vessel types and environmental conditions. So this is a very different approach at understanding how safe a particular type of infrastructure is. So that's a very quick overview of different approaches to understanding probabilities of incidents. So just as a quick summary, we can say there is value in understanding navigational risk. You're trying to prevent loss of life, damage to infrastructure, damage to vessels, and trying to mitigate that at an early stage is advantageous. The marine environment is very complex, so these risks are uncertain. But there are different approaches beyond just the expert judgment of the people involved to try and analytically understand these problems and try and put quantitative numbers to likelihood. But I'll be the first to admit that these models are also imperfect, just like human judgment is imperfect. Whether it be the costs, the quality of the data, there are problems that need to be overcome. So therefore, probably the best way to do it is to mix the two. So you want a mixture of marine expertise who understand the environment with scientific models that are able to put numbers to things. And from that, you probably merge them together to come up with a pretty good answer. So that's it. Thank you.
Thank you, Andrew. Confirm my suspicion that statistics can demonstrate that any reach of the Thames is the most dangerous.